right. Oh, and for those of you who know Shiva, I was over at his place for dinner last night. He says hi. One of the things where and if you don't know who I'm talking about, I think I've mentioned him before. He was a MSIT student 8 or 9 years ago, a while ago now, and he's now married to an American girl and works as a software engineer, but he's working on starting a consulting business where he wants to help international students find sponsorship-based jobs here in the United States and things like that. So we're going to try to get him in to give some sort of presentation at some point in the next, semester or so, to kind of talk about those things. So hopefully we can bring some opportunities from that, because he's gone through that whole experience. Okay, so let's start with the discussion from the homework. So we're starting to talk about the actual assembly language of our architecture and things like that. And so for your homework, you were to look at the decimal versus binary versus octal versus hexadecimal. Why do we use all of these different bases when it comes to computing? Anybody want to take a first stab at that, and then we'll talk about it?
Well, basically, computers don't understand every language. They only understand a certain form.
Okay, so they understand binary, right? So at the base level, computers are going to understand binary, zeros and ones. They're digital logic, on and off. So we're going to say binary. Computers understand this at the all right. So computers understand this at the base level, since binary, which is base 2, supports exactly 2 states, 0 or 1, which directly mimics the 2 states of digital logic, on or off. All right, so that's why binary makes sense. All right. What about octal? Well, so let's throw decimal in there. Decimal is the other easy one. Okay, so if binary is is what computers understand, decimal is what humans understand. So when we talk to a computer, perhaps through an assembly language, we will prefer to use decimal values and let the computer do the translation. Now, the reason the computer has to do the translation, so if we say, let me just do this on a separate slide. Okay, so if we say on a separate slide here, why does the computer need to translate from decimal to binary? Maybe the human being, maybe we want to put the value 71 into a hardware register. Why does this need to be mapped to, let's see, what is that? What's the ones, twos, fours, eights, 16s, 32s, 64. So that is 72. Nope, that's not going to get us there. 64, 68, 70, 71. Ones, twos, fours, eights, 16s, 32s. All right. So why do we need to map from that 71 in decimal to something that looks like this? If our goal ultimately as a human being is to get this number stored into our variable made out of hardware that sits on the processor, why did that translation actually have to happen? Tell me about that. You'll have to unmute yourself because I muted everyone, so we didn't have all the background noise. Does anybody want to take a stab at why do we actually need, when the human being says, I want to put 71 into register 3, why did the computer have to turn it into this? We got nothing.
Does that have to do with all the switches and how each kind of represents a part of memory?
Well, it has to do with how memory works. So let me ask you this then. What does a hardware register look like? So at the end of the day, a hardware register is going to be, 16, 32, 64-bit registers. And these are implementations of memory technology. When we say a register is 16 bits, what we are really saying is that it is capable of holding 16 individual zeros or ones. Okay, so we can really think of a hardware register as 16 individual little buckets if it's a 16-bit register. If it's a 32-bit register, it has 32 individual little buckets. And each of those buckets can hold a single bit, a 0 or 1. Now, the way it holds it is through electricity, and this is how memory architecture actually works and that kind of stuff. So it has to, when the computer's turned on, it maintains enough charge to either keep a bucket at a 0 or keep a bucket at a 1, that kind of stuff. But ultimately, the way it holds a value, it's holding numeric values. It holds those in a state that requires it to be described to the computer in either zeros or ones. Now, on one hand, we can say, well, that's because that's the way the computer wants to use them eventually, and that is a true statement. So that's a happy coincidence that that we have to store the value inside of the registers in binary, and the computer just happens to want to use them as binary. That's a good thing. But at the end of the day, the real reason that we have to store them in the registers in binary is because that's how memory is built. Okay, memory can hold a whole bunch of individual parts of a number, but this does also then have a caveat. So this caveat is we do not have to use a register to hold a single value. We can choose to hold more than one value at the same time in a register. All right, and the reason I bring this up is this is kind of where human problem solving comes in. Say, what do humans do? If I give you 16 little storage containers, do you have to put all of the same stuff in each container? So let's say at your house, you have like the Tupperware containers, and I give you 16 little Tupperware containers, you know, for keeping leftovers and stuff like that. Do you have to put the same stuff in all 16 containers, or can you put mashed potatoes in one and you know, leftover chicken in another one? You know, you could put different stuff in different containers, right? That seems obvious to a human being. All right, now let's assume I'm going to link all those containers together. So even though there's 16 individual little buckets, you know, they're all connected. So you have to carry them around all at once. That's fine. So it's, you know, it's just kind of a weird thing. But you know, you can choose to put you know, 16 individual eggs, one per container. You could do that. You can hold the same stuff in each of those containers. But as human beings, we problem solve. We say, oh, I have 16 containers here. I can do whatever I want with those containers. But what I do to those containers might have a side effect to it. So for instance, if I put something that needs to be refrigerated in some of those containers, well, I'm going to have to put all the containers into the refrigerator. That's going to have consequences to that decision of me choosing to store certain things in that container. Now, human beings also have the advantage. You know, this goes back to, you know, how do human beings solve problems? We ask questions, repetition, and our memory. And we take for granted how good of problem solvers we are because we have trouble articulating how we're actually solving those problems. So if I say, oh, I want to get the egg from the 5th container, a human being just glances down, counts to the 5th container, and grabs the egg from it, right? A bunch of stuff actually happened in that process that we didn't even think about, right? It just sort of happened. We're smart critters, and we just figure things like that out. So humans can put different things into the different containers, and we can easily remove or look at individual containers. We don't necessarily know how we do it. It just seems easy to us. All right. So with that in mind, I'm going to do a simpler example here. So let's say I have a 8-bit register like this. All right, so in an 8-bit register, duplicate this guy, give myself a couple of 8-bit registers. In an 8-bit register, I can store a single value like that. So that's the number 71 that I have encoded into binary, and I'm using those 8 bits to store the number 71. And notice that before my 64th power here, I have a 0 there. So I've padded it out on the left. That does not change the value of it. This is the 1s place, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, the 128s. So I have 0 in the 128s, 1 in the 64, 0 in the 32, 0 in the 16, 0 in the 8, 1 in the 4, 1 in the 2, 1 in the 1. You add all that up, you get a 71. Okay, so I can store those values in there. And then when I read from that register, I want to read the entire value of the register. Similarly, though, what if I want to store, let's say a 13 and a 27. So 13 would be 1 in the 8's place, 1 in the 4's place, 0 in the 2's place, 1 in the 1's place. That's 8 plus 4 is 12 plus 1 is 13. Let's see, I'm not going to be able to get to a store 15 since I'm only dealing with 4 bits. Actually, let's store a smaller value. Let's store 5. So this will be a 0 in the 8's place, a 1 in the 4's place, a 0 and a 1. For the number 5. All right. So I can choose to say I want to put 2 different values like this, 2 different 4-bit values into a single 8-bit space. Now, we can talk about how to get the values in there. We'd have to meld those 2 numbers together somehow, but I'm going to focus today on how do we get the numbers out. All right. So I'm going to somehow magically get those values in there. So we're going to throw them in. Okay. So now stored in those 8 bits in that register, I have 8 individual bits, but we happen to know that as human beings, we've decided to use those 8 buckets in an interesting way, where we have 4 of the buckets used to hold one number and another 4 of the buckets to hold a different individual number. Now we can go even, we can go even more granular than that, and we can have, they use this for like masking or switches, where you can have each individual bucket only hold a single number, and that number might mean something. Maybe this bucket means whether or not the sound is on or off, and this this bucket represents whether or not a certain light is on, and this is another light and another light, stuff like that. So you can use these buckets to do all sorts of things. It doesn't just have to hold a number. All right, and that's the big point I want to get across here is, as problem solvers, we have these hardware registers, and it's not just for doing math. We can use it to hold data. We just have to have we have to have an interesting way of working with them. Okay, and that's what I kind of want to talk about here next. So if I want to get this value 71 out of this register, I just read in its entirety the contents of that register. Easy peasy. I just read the value. Okay, so I can store that value into memory if I want to do something like that, and I've done it. But in this example here, if I want to get at just that value, or I want to get at just this value, I'm going to have to do some interesting stuff in order to accomplish that. So we need to look at a couple of operators. we're going to introduce something called bitwise operators. All right, anybody heard of bitwise operators before? And what are they? Can anybody tell me what the bitwise operators are? Got nothing? We got a lively group. All right, so we have bitwise and. Typically, the bitwise and in our modern languages is represented as a single ampersand. We have a bitwise or, which is typically represented as a single vertical bar. Let me put some spaces in there. All right. There is a bitwise XOR, which in our modern languages is typically a caret like that. So if you're learning, high level programming, sometimes you want to put the caret somewhere to say, like 3 to the second power, something like that. But this is actually taking the number 3 and bitwise XORing it by 2. So that's it's solving a different problem. It is going to give you an answer, but it's not going to give you the answer you expected. In most languages that use the caret for the bitwise XOR operator. We then have bitwise left shift. That's usually that guy. And we have the bitwise right shift. That's usually that guy. All right. And there might be some other bitwise operators or some, more powerful versions of the shifts to let you more conveniently do stuff in some languages, but let's just leave it like this. This lets us do things with this. So let's look at a bitwise and. So let's say I wanted my number, I used the example before, the 3 bitwise and 2. All right, so I'm going to go ahead and write the 3 and the 2 out in bits. So a 3 is a 1 in the 2's place, a 1 in the 1's place. And a 2 is a 1 in the 1's place, 1 in the 2's place, and a 0 in the 1's place. So this is the number 3, this is the number 2. And when we bitwise XOR, I'm sorry, I'm going to bitwise and these. When we bitwise and these guys, what I'm doing is I'm going to apply the and operator per bit. All right, so and says 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 0 and 0 is 0. So the only way for an and to be true is for both bits to be a 1. So 1 and 1 is a 1. 1 and 0 is a 0. So that means 3 bitwise and 2 gives you a 2. So this guy equals the number 2. Now it's probably not clear why we want to do that yet. And that's because we're currently operating at decimal numbers. Once we see this at the binary level, it makes more sense. That'll be our punchline for where we're going here in a few minutes. All right, but just at the math problem level here, do we understand how I took 1, 1, which is the number 3, and the number 1, 0, which is the number 2, I bitwise anded them together to give me 1 and 1 is 1, 1 and 0 is 0. And that happens to be the number 2. So if I were to print out in a modern programming language, 3 and 2, it would give me a 2. All right. If I want to do a bitwise or, I'll put an or symbol there. Same numbers we're dealing with. 1 or 1 is 1. 1 or 0 is also 1. So this would give me a 3. So now we're applying the OR operator to these guys, and OR says one or the other or both. So at least one of these of the 2 bits in question needs to be a 1. If at least one of them is a 1, the answer will be a 1. A bitwise XOR or exclusive OR exclusive OR says one or the other, but not both. It's exclusive. So in order for an exclusive OR to be true, exactly one of the bits needs to be a 1. So that means one exclusive OR 1 is a 0. They're both a 1, but for XOR to work, only one of them is allowed to be a 1. And then one exclusive OR 0 is a 1. So this gives us a 1. Now, I would say in our discussion today, just to kind of give you a hint, we're not going to be using XORs very much. This is more just academic. I'm throwing in that extra operator. Okay. But the punchline I want you to see here as we're going through these is the word bitwise is really talking about us taking 2 values and applying an operator to a single bit on one value to a single bit on another value. So we're doing it on a bit by bit basis rather than to the entire value. All right, that's what we mean by bitwise. Okay. So let's do a left shift, this guy. So let's say we want to say 3 left shift 2. That's going to be the number 1, 1. And we want to left shift this guy 2 times. Now, what that means is we're going to be moving it to the left twice, which in this case is going to ultimately give us 1100. All right, because we shifted it to the left. We started off here. This one moved to the left, which brings a new 0 in here. This one moves to the left again, which brings another new 0 in there, and everything shifted along with it. So now this number here was a 3. This is the 1s, 2s, 4s, 8s. So this is a 12. So when we left shifted, what do? Every single time we left shift, we're multiplying by 2. 3 times 2 is 6. 6 times 2 is 12. All right. So that's what a left shift does. Left shift allows us to multiply the current value by 2. Might be handy. Again, don't necessarily try to think about why you might want to do this. What you're thinking about right now is that you can do this. And where I like to connect this for human problem solving is, imagine you run out to Home Depot, you bring home a hammer. Now, you might say, okay, well, this hammer maybe has an intended use, but I can use this hammer for all sorts of different crap. And when some problem presents itself and I'm trying to think about the solution for it, I might say, oh, I wonder if a hammer would help with that. This is that same kind of thing. This left shift, it does a thing. And what that thing it does, doesn't necessarily say this solves this exact one problem. It just happens to work a certain way. And what we're seeing here in the big picture is that it multiplies an entire value by 2. Okay. A right shift this guy. All right, so if we right shift 3 2 times, we start off like this, and we drop off that first one. He shifted to the right, so he fell off the cliff. That was the first left shift. Then we, and keep in mind that, so 3 left shifted once, made it a 1. So that's integer division by 2. How many times does 2 go into 3? Goes in 1 time. So 3 divided by 2 is 1. If I right shift it again, this one falls off the face of the earth. So 1 divided by 2, 2 goes into 1 0 times. So we're left with a 0. So right shifting is dividing by 2 each time, but it's doing integer division. Okay. So those are our bitwise operators that I want to introduce this morning. Here, let me stand up here. Stretch the legs. All right. All right, questions about any of those operators? Not what would we use them for, just do you understand each individual little tool that we just put out there and how they work? Not what we would use them for.
Could you repeat your explanation on the right shift? Because I kind of feel like I missed a step here.
Okay, so right shift, when we shift to the right, I mean, when you have a number, a binary number, there's like a cliff over here on the right-hand side.
Mhm.
So when I shift this 1 1 to the right, the very first shift to the right gives me a 0 1 0.
Okay.
Actually, I'm sorry, it gives me a 0 1.
Okay. Yeah.
This far one fell off the cliff. We lost them.
Mhm.
Giving us just this one, but because we shifted to the right, we pad the other side with a 0. Then when we shifted right again, this number fell off the cliff.
Oh, okay.
And we got the other 0 0.
Oh, okay. That makes more sense now.
All right, so whenever we move binary numbers to the right, new zeros will fill in on the left, because that doesn't change the magnitude of the value, but we will lose values. So let me go to this, a bigger picture. If this is my register right here, and I shift all of these numbers to the right, this guy has no bucket to go to. We just made him jump off the cliff. Make sense? When he shifts to the right, he jumps off the cliff. If we shift all these guys to the left, we lose that dude, but all these other numbers move to the left and we fill in a 0 here. Okay. But the hope is that, you know, and that's something to keep in mind, is if you only have 8 bits, let's say I have a number like this. So this is the, well, let's assume that I'm not holding 2 numbers in here. Let's say this is one big number. This is what, 1s, 2s, 4s, 8s, 16s, 32, 64 is 128. This is 128 plus 64. Plus 16. Plus 4. Oh, here, let's just get it to that. That's 208. Plus 4 is 212, 213. So this is the whole number 213. If I shift this guy left, then everything is going to move left here. And I'm stuck with that. But the original one that we had here, he fell off the cliff. So we actually lost the value. He's gone. So if we read from this register again, this is the 128 plus 32 plus 8. 128 plus 32 plus 8 gives me a 168. 71. This is 170 now. So this did not ultimately give us a final value that was twice what it used to be. If I had space for this guy, so this number is twice what the number used to be. We did multiply by 2, but because I'm storing this in an 8-bit register, it only has 8 buckets. All right. I overflowed my far left bucket, and this thing just fell off the cliff on this side, which made me lose magnitude. I lost value from that. So I didn't get the multiplication problem done. I don't have enough bits to hold the number that it would have become. You know, it's we see this in high level programming all the time, where, you know, you take a byte. If you have an integer type that's a byte, that's an 8-bit signed number. So it can hold values in the range of -128 to +127. So if I put a 127 into that guy and then I add 1 to it, that becomes a -128. Well, why? Isn't 127 plus 1 a +128? It sure is. But what did we do? When we added 1 to it, we did some binary math and we ended up losing a value, which made us circle back because we didn't have the bits to the biggest signed number. The biggest positive signed number we can hold in 8 bits is the number 127. We cannot hold the number +128 in 8 bits. We would need 9 bits for that. Okay, make some sense. So we are up against, this is just, again, problem solving constraints. We have 8 buckets that we're working with in our examples here. That means we can store exactly 8 zeros or ones. So if we do something that would require us to store 9, we're out of luck. You know, going back to my Tupperware example, if I give you 8 containers to store leftovers and you need to store 9 different things, you're going to be throwing some stuff in the counter. you're not going to be able to fit your 9 things in those 8 buckets. This is just kind of the rules. Okay, so we are messing around with that kind of thing. Okay, so we are limited by the containers we're working with, but in general, when we do a left shift, we're multiplying by 2. When we do a right shift, we're dividing by 2. And then bitwise ands and ors, or XORs, or XORs, some people call it. You know, those are doing what I would typically call masking. And that's kind of where we're going with this. All right, so any other questions about any of those bitwise operators? Again, not what we're going to use them for at this point. We're going to try to stumble into that here, but more about, you know, that this is how this little tool works. You've probably seen this stuff before. When as like a present, you get one of those multi-tool toolkits, and you know, several of the tools that are in there, you know what they're for, like the various screwdrivers and stuff. But there's always those 1 or 2 tools that you're like, well, what the hell is this for? You can't imagine what it's for, but like, okay, well, I'll keep it in mind, you know, in case I need it to pry something or whatever. You'll find a use for it for something. Okay, so now getting back to our example over here, where we have 8 buckets. And in this example, I'm storing 1 entire value, the number 71, in my 8 buckets. And if I want to make the 71 a 142, I can left shift it. I have room. Okay, so I can store the 142 in that guy. Now you might ask, actually, here, this will be an interesting thing. I just said that in 8 bits on our high level computers, you can hold the numbers -128 to +127. Well, I just said that we can left shift this. And now this is the number 141 or 142 rather. We multiplied the 71 by 2. But and this is 8 bits, right? This is 8 bits. I just said that the most in a high level programming language, the highest value you can store, the highest positive value you can store in 8 bits is a 127. So you can store between -128 and +127. Yet we're seeing right here that, oh, I can store the number 142 in 8 bits. Is Littman lying to me? Anybody have an explanation why I'm able to do this in this case? When I'm telling you in a high level programming language, 142 will not fit in an 8-bit integer. See, this is kind of where architecture starts getting fun. It's when I get your mind moving away from just doing math, just holding numbers, because we're looking at interesting ways to use those 8 bits. We don't have to use them to just hold a value. When you're using a high level programming language and you create a byte, the byte data type in like C or C++ is a signed number. So we have 8 bits to work with. We have a total of 8 buckets here to work with, but we've decided that we want to be able to keep track of positive and negative numbers. So that means that using only those 8 buckets, we need to somehow figure out how do we also incorporate the sign, whether it's positive or negative in there. And we do that through something called 2's complement. Let me at least introduce that on a slide. I don't want to lose our pace here too much. So I have something called 2's complement, and this is a mechanism for storing positive and negative numbers in binary. We encode negative numbers in 2's complement, which then means we need to decode the actual value when we read the number. And maybe we'll eventually talk about, maybe next time or something, we'll actually look at 2's complement. Competitors to this are sign, magnitude, as well as 1's complement. Both of these suffer from the 2 ways to represent 0 problem. We do not need a positive 0 and a negative 0, but both of these competitors have that, which means that there's one more number that we're not able to store. So with 8 bits, we can store 256 unique states. Again, move it away from numbers, move it away from math. We can store 256 unique organizations of 8 ones and zeros. If we want to use that for math numbers, like to represent the number 1 and 2 and 3 and 4 and 5, we can represent 0 to 255. If we then also want to support negative numbers, well, now the 256 unique states is going to take us to negative 128 to positive 127. We're going to be having to do something with one of those bits to keep track of the sign. But if we just use the far left bit for positive or negative, now we can do, negative 128 to positive 128 because we're using one of those things, but we have two representations of 0. We have a positive 0 and we have a negative 0. Seems like a waste. We don't need two different zeros. We only need to represent 0 once. So 2's complement allows us to encode a number where we only have one representation of 0, which then gets us an extra value on the negative side. That's why it's negative 128 to positive 127 for signed numbers. But back in our example here, a 142 can fit inside of 8 bits if we're treating this guy as a unsigned number. We're not keeping track of positive or negative here. So that means I can hold up to the number 255. 0 to 255, that's 256 unique states, unique numbers I can store here in 8 bits. Okay. So this guy is pretty straightforward. If I want to read this number, I don't have to do anything special. I just read the entire hardware register and I can do stuff with it. But this second one here gets a little bit tricky. We've decided to be clever. As humans, we decide, you know what, I need to store the number 13 and I need to store the number 5. Well, why use 2 separate hardware registers for this? When I could, since both of those can be represented inside of 4 bits, I could use 4 of the bits for one of the numbers and the other 4 bits for another number. So here is my 13. Here is my 5. And we're not going to worry about how we got those numbers in there in our example here. But now I have this register, this 8-bit register that happens to hold 2 numbers. And I want to be able to extract my 2 numbers from that register. How would you suggest we do that? Using my bitwise operators. How do I make this guy look like this? And similarly, how do I make the same value look like this? So that when I read from it, I have this is my number 5 is this one, and this is my 13. So I need to somehow go from this state for 8 bits, and I need to turn it into this. Secondarily, I need to take that same starting state and turn it into this. How do I make this collection of bits turn into this? Let's just focus on half the problem. Because what I'm trying to do is I'm trying to take this entire collection of 8 bits and I'm trying to extract my 5 from it. So I need to somehow morph this guy into this. Any suggestions? And the answer- go ahead.
Just an idea. Is there any way to like kind of break them in half and use a combination of the right and left shifts?
We're not going to be able to break them in half.
Okay.
So,
got it.
so our hint would be you're going to have to use some of those bitwise ands or ors or things like that to do this. Shifts are going to be involved here shortly, but yeah, so really think about it like I need to turn this into this using only the tools we've introduced today. Let me ask us a sub question of it. How do we guarantee that we get zeros?
Using an XOR? Okay.
How would you use an XOR to guarantee zeros? XOR says one or the other, but not both.
Yeah, that's kind of our, yeah, but I see the problem. So but I mean, when I said that, I immediately saw the problem there because it's immediately the first. I mean, it works for like 1 and 1, but yeah.
All right, so I'm going to perform some kind of bitwise operation between these two. What can I put down here? And let's, for right now, let's just focus on these four. So what can I put down here and which bitwise operation can I do to guarantee I get all zeros here?
You could do and.
Okay, so I can use the bitwise and. So bitwise and operator, but what do I need to put in here?
You put 0, you put the opposite number of, if you want a 0, you can just put the opposite number, and if you want that number, and if you want to have that number, you
But
make
we
it,
don't
yeah.
necessarily know what these numbers are, so I can't operate off the opposite. But what can
Oh,
what can I just put in here to guarantee I get zeros?
0.
Zero. So if I put a 0 here, it does not matter what these numbers are, right? If I'm using a bitwise and, if a 0 is involved, I end up with a 0. That makes sense? Now, if I'm still using a bitwise and, what can I put in here to maintain whatever these values are? I don't want these guys to change because I want to be able to ultimately read from them. Whatever's on the far right, that's what we're going to be reading from. We can pad numbers as far as we want with zeros on the left, and it doesn't change the value. So the second part of this is I want to put numbers in here that when I bitwise and it, I maintain these exact values. What can I put down there?
One.
Okay, so if I put ones in here, a 1 and a 0 is a 0. A 1 and a 1 is a 1. A 1 and a 0 is a 0. A 1 and a 1 is a 1. So bitwise anding with ones maintains whatever the original guy was. So if I want to extract just my 4 right bits, I can do a bitwise and give it zeros where I want to zero it out and ones where I want to keep the value. This is called a mask. So I'm taking this number and I'm masking it by this seemingly arbitrary type thing. But because I know how the tool works, I'm going to be left with this value, which is my 5. All right, makes sense how we accomplish that. But now we need to accomplish the other side of this. So let me scooch everything up so I have a little bit more space. All right, so now, again, here's my original value that's storing both the 13 and the 5. And I need to do something or some things, plural, hint, hint, to turn this guy into that guy. So what can I do? Notice here that these 4 bits ultimately will be over here. So what can I do to this guy to be able to read my 13 from it down here? That's what this is. This is 13.
Right shift.
You want to do a right shift?
Yeah.
Okay. How many right shifts?
4.
4 right shifts?
Yes.
If I do 4 right shifts on this guy. So if I take this value and I right shift it 4 times, that's going to keep moving these things over, leaving me with and filling in zeros on this side. And as I was doing that, that 1, that 1, that 0, that 1 came over. So I right shifted the stuff off over, which made these 4 things, since I did it 4 times, fall off the cliff. Right? Made those things fall off the cliff and leaving me with something like this, which I can then read, and that's a 13. So I can then grab those left values by moving them into the right position without losing without you losing magnitude. All right. Now, just for the sake of argument here, let me just steal this real quick. Zero out first. how do I get this result? How do I go from this guy to this guy, where I've maintained the left 4 and I've zeroed out the right 4? We solved this problem basically a few minutes ago when we did it for our top number.
4 ones, 4 zeros.
Okay, so we're going to do a bitwise and we're going to say, I want to keep whatever it used to be. So whenever we bitwise and with ones, we're just saying keep what it used to be, whatever it is. If it was a 1, we're going to keep the 1. If it's a 0, we're going to keep the 0. And when I want to zero out what it used to be, I bitwise and by zeros. So bitwise and, just that little tool in and of itself allows us to manipulate portions of a register, which is valuable because it's going to be common when we want to use a single hardware register to store multiple pieces of information. Because with computing, we're not always storing gigantic numbers. And we are limited by our architecture. Our processor only has so many of these hardware registers in it. It only has so much L1, L2, L3 cache. We don't have an infinite number of memory, an infinite amount of memory. So we want to be as efficient with our memory as possible so that we can work with these values. And if we have these primitive bitwise operators that kind of allow us to sling bits around, you know, that can be a pretty powerful thing. Okay. And there's similar tricks with like bitwise ORing. Bitwise ORing kind of lets you meld two numbers together. Where you'll often see it in computing is you'll have, like I said, in 8 bits, you can have 256 unique representations of ones and zeros. So 256 unique states you can represent. Well, let's say that you have 2 different states, like maybe one of them is like read and the other one is write for like permission on a file. You can take the state for read and the state for write, you can bitwise OR them together, giving you a new state, and that new state is the unique representation for read and write. Something like that. And you can do that by bitwise ORing 2 known individual states. So these are all just manipulation of bits. Okay. So we've been talking about hardware registers here, and I just want to take a quick peek. I'll make sure I give you enough. I don't need to quite give you enough for your homework, because I made the homework due next Tuesday, because we're just getting into the assembly language stuff now. All right, so we've been talking about hardware registers today, and these are effectively, you know, physical Tupperware containers that are connected to your processor that can hold some number of bits. We've been messing around with 8-bit ones here because that's nice and convenient for us to fit on our screen. But typically our hardware registers in a computer these days are going to be 16, 32, 64, and even 128 bits, depending on the computer. And sometimes they actually have registers kind of playing double duty. You might have a 64-bit register that can also individually behave as two 32-bit registers to kind of make what we just did even a little bit more convenient. You can operate with a high and low portion of the 64-bit register to give you the left 32 bits or the right 32 bits. Same thing with 16-bit registers that would allow you to more conveniently store numbers in the left and the right without having to use as many kind of bitwise tricks to put numbers in or get numbers out. So that is some conveniences that are built in there. But at the end of the day, they're just giving us power tools for something that we can pull off through, I guess, bit slinging. Let's call what we're doing today bit slinging. That's when I think computer architecture starts getting fun. You know, and what I hope that we've kind of accomplished today, especially for those of you who went through our undergraduate 325 class, is connected some dots. One difficult thing with computer architecture, and I do teach it differently. And like I said, grad classes are a little bit weird since we have to do a lot of reading and kind of writing stuff because the nature of our student is that some of you don't necessarily have backgrounds in computer science. And you might say, well, then is this class actually easier than the undergrad class? Well, I would actually say not necessarily, because all of you, even though you might not have a background in computer science, you have a maturity in learning. And by us saying that you have a master's degree in computer science, what we're really saying is that you've taken your maturity in learning and you've expanded your overall knowledge so that now you have more tools that you're aware of to solve complex problems. You'll go and figure out how to solve them then because you have a maturity in learning. So a master's degree is giving you less of an applied skill set and more expanding your knowledge of those undergraduate classes. So hopefully those of you who have had the undergrad classes are kind of seeing some of that as you're looking into the stuff at more depth. And, you know, and one issue you run into, or at least that I've heard from our 325 students, which is the undergrad architecture class, is, you know, you're learning all these little things and you don't know why. Like, why would I ever need to know this? Why would I ever do this? Well, hopefully you've seen some practical things today that's like, okay, I mean, that doesn't necessarily seem like something that happens twice a week. But you know what? That's something that I could practically put towards, oh, what if I need to store two numbers in one register? Well, now you have some skills that let you do that. On the flip side, you know, why do these bitwise operators even exist? Why do the shifts even exist? Well, hopefully you now have some practical knowledge of that. Let's see. So when we're dealing with registers, we really have, we typically are storing instructions. So when a CPU is, you know, we're thinking about the computer processor as a whole, and that guy does number crunching, he does problem solving, and he does things in terms of, when we first talked about it, in terms of the magic tricks he has available to him. All right, so our CPU has this big list, this menu of things that it knows how to do. And each one of those things isn't overly impressive in and of itself, but if it does enough of those unimpressive little hand waving things in a row, actually something magically has happened. All right, and and we rely on our processors to be really, really, really fast. So part of that has to do with them getting as much stuff squeezed into those registers at any point in time, because those hardware registers, that is the fastest communication channel that includes storage that is possible on our computers. The closer you are to the CPU, the faster the memory, but probably the more expensive per bit and the smaller capacity you're going to be dealing with. The farther away from the processor you get, you start getting larger amounts of storage, but you're trading off the speed at which you can access those values. So the CPU really feeds off of its registers. So it fetches the next instruction into a register. It then decodes that instruction to which magic trick it's actually asking it to do. Then it actually executes the instruction. That's when we toss it to the actual CPU and it does its thing. Okay, those are the states, and that's how we feed off of those registers. Let's see. Is this in our? Yeah, so you previously looked at a paper dealing with recent ARM processors. Well, I suggested you pick a recent ARM processor. I don't necessarily care as long as you now have a good concept of the things that make up these processors. Specifically, ARM is going to be kind of what we're looking at a high level architecture. So what we'll start looking at next time is the specifics of ARM architectures. And while they're not all exactly created the same, they all are based on the same premise. So Apple has their own processors. We've looked at their AX chips and their M1 chips. These are all ARM processors. And we've also looked at, we didn't look at it, but we talked about the Qualcomm Snapdragon processors. They're both ARM architecture, just from competitors, and most of the stuff we're talking about in here translates between the two. We don't need to, talk about the individual little details. So a lot of the stuff from this we've talked about. So we'll start with this slide next time with an ultimate goal, and you can start looking at it now if you'd like, is for next Tuesday, you're going to write a little bit of assembly code, that loads some numbers into 3 different variables and then reverses those variables in memory. So you're going to be manipulating some hardware registers to represent storing 3 different numbers and then turning those numbers around and stuff like that. Okay, so not real hard assembly, but again, what I'm saying in here is we're learning those skills that you're going to be able to apply to larger problems. And part of it's going to be kind of, looking at what's under the hood in an ARM architecture. So if you want to get ahead, you can go ahead and start doing this. This is not going to be an overly difficult assignment, but we're going to get into some more of the details of this on Thursday. All right, questions, comments, concerns, bribes. Okay, I'll get caught up on the grading from the last 2 assignments, hopefully today and tomorrow. Like I said, you actually don't have an assignment due on Thursday. The next one I may do on Tuesday because it's going to take us some time to get through this, but feel free to go ahead and get a jump start. Otherwise, I will see everybody on Thursday.
Take care, Professor Lehman.
Yep, have a good one.